Good afternoon, class. Here's practice test number 2 covering chapters 4 and 5. Chapter 5, discrete probability distributions. Starting with the first question, does the table describe probability distribution? What is the random variable? What are its possible values? And are its values numerical? That's really the bottom line. As you look at this one, X as the value 0, 1, 2, 3, which represents number of gears, and P, or the probability P of X, has numerical values. So here's a couple of things. Number one, the variable X, which is the number of gears in the three birds, 0, 1, 2, 3, is a numerical random variable, and its values describe probabilities. So these are the probabilities. Summation of P of X. So this column, if we add them up, they must add up to 1. So that is one of the criteria. It has to add up to 1. The only time it may not, if we have a round of error, so the result may be 1 point, bunch of zeros and then 1, or 0.99999. That really means it's 1. It's been due to round of error. The next one is that each one must be between 0 and 1. We can have a negative probability. We can never have a probability larger than 1. And all criteria are met. So the answer is yes. All criteria are met, and the answer is yes. In a game, you pay 60 cents to select a 4-digit number. If you win by selecting the correct 4-digit number, you collect $3,000. How many different selections are possible? Well, the number of digits are 10 because the numbers go from 0 to 9 and represent the number of digits. There are 10 of those. So there are 10 possible numbers, and there are 4 spots. Each one could take 10 different values. So they can repeat. There is no restrictions. 10 to the power of 4 or 10,000 is the answer. What is the probability of winning? By definition, probability is n of winning over n of s. So simply there is one way to win. So 1 out of 10,000. If you win, what is your net profit? And it's important to pay attention. In a case like that, we've already paid this much. So we are out of 60 cents. So if we win, however amount we win, we have to subtract this number from it. So the net profit is the money gained minus the investment. So $3,000, how much did we invest? 60 cents. So it's $2,999.40. Write the probability distribution of net profit if you win. Well, here's the numbers. $3,000 if you're a winner, otherwise losers, and the total. So how many can win? There's only one of them. the total is 10,000. So everybody else will lose 9,999. So that's the first column. There's only one way to win, so there's only one winner, total of 10,000, right? So the rest would be the number of losers. Now, how much do we gain? The person who is winning is going to gain this much. What about the loser? We're going to write negative, whatever this number is, 0.6. So this is for the winner, and this is for the loser, and you have to put the negative. What is the probability? Over here is 1 out of 10,000. So over here would be 9,999 over 10,000. Those are the probabilities. Now this is a very important table, the probability distribution of net profit. We are going to continue on that thoughts. And the same question now, the same question, we want to find the expected value and the interpretation. What does it mean? So these are the formulas that are available to you. As I mentioned, you have a formula sheet. Mu is summation of x p of x, and then sigma squared, which is the variance. Mu is the expected value, e of x or mu or the average or the mean. Sigma squared is summation of x squared times p of x minus mu squared, or the summation of x minus mu quantity squared times p of x. Now, we're going to use this table, and we're going to make up a couple of columns here. We need x times p of x. We need this column times this column. So let's multiply these two numbers. Let's multiply these two numbers. So x p of x, let's multiply these two. Let's multiply these two. When we multiply these two, we get 0.29994. When we multiply these two, minus 0.6 and 0.9999. This is almost 1, so we almost get negative 0.6, okay? So what is mu is the summation of x p of x. So just add up whatever you have here. Add these two numbers, and that is mu. Therefore, the expected value, or mu, summation of x p of x, ends up being negative 0.3. Now we're going to discuss the meaning in a moment. But let's also calculate this. X squared times p of x, x squared. You're going to raise this to the second power and then multiply it by this number. You're going to raise this to the second power and then multiply it almost by 1. Notice if you raise this to the second power is almost 0.36 times 1 is almost 0.36. I hope you see that. Needless to say, you need a calculator for this. Now, if we add these two, this is summation of x squared p of x. So if we add these two, but to calculate sigma squared, we are going to subtract from this number to the second power. That's the meaning of it, minus mu of squared. So that would be sigma squared, and sigma, and remember, sigma squared is the variance. Sigma is the square root of that. So the square root of this is sigma. This value we have calculated here to be 900 minus mu, which is negative 0.3 quantity squared. And of course, you raise this to the second power, you get 0.09 subtracted from 900, take a root, and it ends up being 29.9985, almost 30. The reason I'm putting a lot of decimals, because if it's not given as to how many decimals, you don't want to take a chance. But I just want to make a point. You go with many, many, many decimals, unless otherwise mentioned. And of course, you want to pay attention. Now, the important thing is, so what? What is the meaning of all of this? So if we have a game that pays 60 cents when you select the 4-digit and you win $3,000, what are these numbers? So on average, a player all players, including the winner, on the average, loses 30 cents or $0.3 per ticket with standard deviation of 30 bucks. Remember, most games, wherever you play, they are beneficial for the house, okay? Its expected value is positive for the house, negative for the player, again, on the average. Can somebody read the question, please? Go ahead. Anyone?
A pharmaceutical company receives large shipments of aspirin tablets. The acceptance sampling plan is to randomly select and test 24 tablets. The entire shipment is accepted if at most 2 tablets do not meet the required specifications. If a particular shipment of thousands of aspirin tablets actually has a 5% rate of defects, what is the probability that this whole shipment will be accepted?
Perfect. It's important to understand what we are dealing with. And remember, in statistics, almost every question is a word problem. So let's write the given. The given is you're dealing with the BD, short for binomial distribution, where N is 24, P is 5% of 0.05. By the way, P is referred to as the probability of success. In this case, could be negative or positive. In this case, it's negative and it's defect, but that's what they call it. Statisticians call this the probability of success. So let's remind everybody what is a binomial distribution. Binomial distribution follows this formula. P of x is Cnx. This is combination of n choose x, n factorial, over x factorial times n minus x factorial, p to the power of x, q to the power of n minus x, where mu is n times p, sigma is square root of n pq, and q is 1 minus p, the complementary event to p. Binomial experiment and probability distribution properties. PD stands for probability distribution. We have n identical trials. It's a fixed number. Each repetition of the experiment, there are n of those. Each has only 2 categories of outcome, like defective and non-defective, good, bad, things of that nature. Precisely 2 outcomes, odd versus even. Probability stays constant, so it doesn't change from one stage to the next, from one trial to the next. And they're all independent, okay? Independent. So let's see what we can write here. We have this formula. We are going to change the n to 24. We're going to change the p to 0.05, and q is 1 minus 0.05 or 0.95. So p equals 0.05, q is 1 minus p or 0.95, and the formula is now this, which all we have to do for any number, replace the x. For example, what is the probability of x equals 0? Replace the x with 0. Remember, 0 factorial is 1. Probability of x equals 1, replace the x with 1. Probability of x equals 7, and so on and so forth. So let's go back to the question now. If at most 2 tablets, that means a probability of x less than or equal to 2. At most 2 tablets. That means when x is 0, it's okay. When it's 1, it's okay. When it's 2, it's okay, but no more. This is the meaning of at most. So basically, you are going to replace the x with 0, come up with the number. The x with 1, come up with the number. With 2, come up with the number and add them up. You don't have to do this by hand anymore. You can use a calculator, and that's my point. It's very important to understand the concept. Set this up, and this is for partial credit. You want to do that. And then you can use a calculator to come up with this answer. So I'm going to show you how to do that, or any technology for that matter. So if you're using a TI calculator, you go with binomial distribution. So how do we get that? Second and bars, binomial PDF. You enter NPX, and if you enter N and P only, it gives all probabilities of 0 to N. If you use binomial CDF, it gives the sum of the probabilities from 0 to X. We want from 0 to 2. So binomial CDF trials, N is 24, P 0.05, and probability of X less than or equal to 2. If you plug in, gives you the answer where you have it here. It is known that 70% of managers of all companies suffer from job-related stress. What is the probability that in a sample of 20 managers, exactly eight suffer from job-related stress? And again, I'm reminding you of what I gave you in the previous page using a calculator. So let's, number one, understand what we have. We have a binomial distribution, BD short for binomial distribution. N is 20. P, the probability of suffering from stress, 70% or 0.7. If you read the question, it doesn't matter how many times, as long as you get this, it's really worth it. Put enough time to write the given. Therefore, we are going to use this formula as it was mentioned in the previous page. And to use that, we need to find Q. P is 0.7. Q is 1 minus that, which makes it 0.3. So P is given as 0.7. Q is the complementary event, becomes 0.3. And now into this formula, we are going to replace the N with 20, P with 0.7, Q with 0.3. So this is the way it looks. Exactly 8. Replace the X with 8. So if I do that, this is 8 factorial, this is 20 minus X, 12 factorial, in any order, it doesn't matter. 0.7 to the power of 8 and 0.3 to the power of 20 minus 8 or 12. And you can put it into a calculator with this format where N is 20, P is 0.7, the X value is 8, and you're using binomial PDF, not CDF, PDF, because you want one value, 8, 9, any number. And that's what you get. And you put it here. And again, when you write it with a lot of decimals. Notice I went up to here and then I changed this one because of 8 to 3. However many decimals they ask you. Especially with the probability, you want to go with a lot of decimals unless otherwise asked. Now we're going to repeat the same question, but part B, see, part A was exactly 8, but this is at most 8. Same question, part B, at most 8. So the very first thing we need to understand the meaning of at most 8, that means all the way to 8, from 0 to 8 and no more. So probability of X less than or equal to 8, that's the meaning of it symbolically. This means this. So X can be 0 all the way to 8, which means P of 0 plus P of 1 plus all the way to 8. Nobody expects you to do this by hand, obviously, because it's very tedious if you want to do it by hand. So use a calculator. So we have number 20 here, we have number 0.7 here, and we have 8. And over here is binomial CDF, cumulative distribution. Cumulative, that's what C stands for. And that's the number. We are going to put this as the answer. And after 8 comes 1. And I'm going to stop at 1. So because it's 6 here, I change the 1 to 2. Next part, at least 9. That means 9 and more. You go all the way to n, from 9 to 20. That's the meaning of it. So we want to distinguish between at most and at least. So we're going to go all the way up to n and happen to be 20. So that's the meaning of it. Now again, you can calculate those and add them up. However, I hope you recognize this means 1 minus the probability of x less than or equal to 8, the complementary event. If we recognize this, so it's 1 minus, this number has been already calculated. I'm going to use that. In fact, maybe even I changed the 3 to 4 here. Again, you go with however many decimals they ask you, and the answer is 0.99486. It's almost 1 or 100%. Again, pay attention to the fact probability. It's always between 0 and 1. Can it be 0? Yes. Can it be 1? Yes. Can't be negative. Can't be larger than 1. Can't emphasize this enough. We're going to continue, and the next part, same question. We are repeating the same question. Now we want to find the expected value. And you recall that mu is NP. So N times P, which makes it 14. So that means if there is a 70% chance that the managers are suffering from stress, out of 20, about 14 of them should be, and it makes a perfect sense, should be suffering from stress. We want to find the standard deviation, and sigma is square root of NPQ. So 20 times 0.7 times Q was 0.3. Becomes 4.2. Now you take a root of that because it's the square root. And the square root of 4.2, if you go with 1 or 2 decimals, perhaps is okay. But again, you want to, I can't emphasize this enough. You want to pay attention to however many decimals they ask you. Would it be unusual to claim that 7 managers from this sample suffer from job-related stress? Well, I hope you remember it was mu plus minus 2 sigma. That's the range rule of thumb. So here's mu, here's sigma. You're going to multiply this by 2. When you subtract it from that number, you also will add it to that number. So when you multiply by 2, you get 410. This becomes 410. Subtract it from 14, you get 9.9. Add it to 14, you get 18.1. If the given number is between the two, is usual. So from 9.9 to 18.1 is usual. If it's outside, it's unusual, and it is outside. This notation, which looks like epsilon, is an element of. When you have a line through it, it's not an element of. That's in set theory. So this means not an element of this notation. Okay, that's the meaning of this notation. Without the line means it is an element. Find the probability of a couple having at least one girl among 3 children. Well, the concept of an at least, we get 1 minus probability of none. And of course, we are assuming that these two are identical and it's 0.5, 50%, 1/2, which in some cases is not. But that's the assumption. So 1 minus probability of a b to the third. And I write this, and this is important because even if they're not the same, let's make it up. Let's say the probability of getting a girl is 70%, and therefore boy would be 30%, you would put 0.3 here. Okay. So since they are the same, one may not know what difference it makes. But if they are not the same, whatever the probability of B or boys are, you put it here. Again, assuming the probability of getting a girl is 70%, probability of getting a boy is 30%, you put 30% here. And so you raise 1/2 to the third power, becomes 1/8, subtracted from 1, it becomes 7/8. And of course, you can change it to a percentage or decimal if they ask you. The second method is to use binomial distribution. Why is it binomial? Because there are two outcomes. So if n is 3 and p is 0.5, right? Again, we are assuming it's 0.5. We're dealing with the binomial distribution, and we are saying at least one girl. So x is larger than or equal to 1, which means 1 is good, 2 is good, 3 is good, and what is not good is 0. That's why we have the 0 over there. So it's probability of 1 plus probability of 2 plus probability of 3. Again, you can calculate that, or it may be easier to use 1 minus probability of 0. It's a binomial distribution. This is the formula everybody has. Now we're going to replace the n with 3. P and Q both with 0.5 or 1/2. So n is 3. So again, you can plug in 1, 2, 3 and add them up, or you can plug in 0, calculate and subtract it from 1. That is a tad faster. Again, you can obviously do it by a calculator, but we calculate the probability of 0. Okay, according to this formula, you replace the x with 0. So if you do that, this is what you get. I hope you realize that this is 1, the ratio is 1, any number to the power of 0 is 1, so it's 0.5 to the power of 3, or 1/2 to the power of 3, or 1/8. So 1 minus 1/8. This one is 1/8. Okay, or 0.125. And what we want is 1 minus that, so we get to the same answer as expected. If an alarm clock has a 0.9 probability of working on any given morning, what is the probability that it will not work? It's a complementary event. Probability of A naught or A complement, sometimes they call it A prime, is 1 minus probability of A. So probability of working is 0.9, that's given. Probability of not working, see with the bar, that's what it means, 1 minus the probability of working, so 1 minus 0.9 or 0.1 or 10%. So there's a 10% chance the clock will not work, which is not good. But here's the idea, and it's called the concept of a quality control. What is the probability that 2 such alarm clocks will not work? Now, a couple of ways to handle this. But for now, the first one is not working. Probability of W1 versus probability of W1 bar. So this represents working, this with the bar represents not working. And two of them won't work. So that means we are interested in the intersection of the two. Probability of the first and, this is the intersection or and statement, second alarm not working. We are assuming independent events, therefore, it becomes the probability of the first one not working times the probability of the second one is not working. There are cases that they may become dependent. For example, if the alarm clock is plugged in and they are both plugged into the same plug and there's a power outage, then it becomes a concept of a dependency. But each one has a probability of 0.1 of failing. 0.1 times 0.1 is 0.01. And this is what I mean by quality control. Although there's a 10% chance that one of them is not working, but there's only 1% chance that they both will fail. Then this concept is used a lot in industry. For example, even when you're dealing with airplanes and jet engines, the engines work independently. So even if one fails, the others can make it. There is a 1% probability that two such alarm clocks will not work. I'm going to repeat the same question, but part C, what is the probability of being awakened if you have two such alarm clocks? So basically, from the previous page, we have probability of working at 0.9, not working at 0.1, and two of them failed is 0.01. That comes from the previous page. It's already done. So the first method is very simple, simply 1 minus that. So probability of being awakened is 1 minus the probability of not being awakened. So the assumption is that means we wake up to the alarm. So 1 minus 0.01 gives us 0.99. So there's a 1% chance it won't work. There's a 1% chance we won't wake up. There's a 99% chance that it works. I mean, the combination of the alarm clocks will work and we will wake up. That's the concept. Here's the second method. We can use the addition method. The probability of A union B is probability of A plus probability of B minus the probability of A intersection B. We have already discussed this. This is called the addition method. Now we are going with two alarm clocks and the probability of W1 union W2. So you're going to change the A to W1, B to W2, and you get this one. So now replace this one with 0.9. This one also with 0.9 minus this one with 0.9 times 0.9. This is W1 intersection W2, not that one. So 0.9 times 0.9. So 0.9 plus 0.9 minus 0.9 times 0.9. And we get the same answer as here, 0.99 or 99%. Here's the third method. We can use binomial distribution where n is 2 because we have two alarm clocks. The probability of awakening is 90% or 0.9. We are again assuming that we are waking up to the alarm. And here's the formula where n will be replaced with 2p with 0.9 and q with 1 minus 0.9 or 0.1. So into this formula, we replace it accordingly. We're looking for the probability of x larger than or equal to 1, meaning if one of them works, we wake up. If both of them work, we wake up. That's the meaning of it. And again, that means probability of x equals 1 plus the probability of x equals 2. Or 1 minus probability of 0. That would make it easier. You have to calculate one of them. Again, this means replace the x with 1, replace the x with 2, all the way to n. N is 2, okay? And so if you plug it into this formula, x equals 0, I hope you realize this goes to 1, this goes to 1. This is 1, everybody, this is 1. And this is 0.1 squared or 0.01. 1 minus that is 0.99. Again, all of them are the same. There are 3 different methods. I hope everybody's fine with that. Same question, part C. Could somebody read this, please?
During an NFL season, there were 256 games played with 1,307 touchdowns scored.
Poisson distribution. Go ahead.
What was the mean number of touchdowns scored in each game during the season? Round the answer to nearest 0.0001.
Perfect, thanks. So class, this is a Poisson distribution. And so let's first see what is a Poisson distribution. Poisson distribution, the probability of the event occurring x times over an interval. The interval can be time, distance, area, volume, or some similar unit, is given by P of x equals mu to the power of x, e to the power of minus mu over x factorial, where e is the base of a natural log, 2.71828. Mu is mean number of occurrences of the event in the intervals. The parameters are mu and sigma, where sigma is square root of mu. And in some texts, they use lambda class. So in some text, they may use lambda, which looks like that. All right, so the very first thing is, now that we have the definition of a Poisson distribution, to find the mean or mu. So the mean number of touchdowns, TD, short for touchdown. So TDs in each game is the number of touchdowns divided by the number of games. So we have this many touchdowns, we have this many games. So this number divided by this number is the average. And we use with a bunch of decimals here. This is important. Although, remember, the number of touchdowns is a discrete value. So if we were to round it accordingly, would be 5. But we want to keep it with many decimals for the sake of calculations. Okay. So when we go with this formula, we are going to replace the mu with the number, and of course, again, as many decimals as possible. And this would represent the Poisson distribution. Now, on January 10, 2010, the Green Bay Packers and Arizona Cardinals played a playoff game in which there were 13 touchdowns scored. What is the probability that a random game would have that many or more touchdowns? So simply put, we want the probability of X larger than or equal. that many, that means equal or more, greater than. Now again, this means start from number 13 and go to 14, 15, okay? And sky's the limit. But we write it as 1 minus the probability of x less than or equal to 12 because this is much easier to calculate. And again, you don't have to use a calculator. The very manner that we calculated the binomial distribution is similar to that. We go with the second vars or variables, pass on PDF, enter mu or lambda or x. This is what I meant. In many texts, they use lambda instead of mu. So in this formula, instead of mu, they may use lambda. Enter or paste. If using Poisson CDF, it gives the sum of the probabilities from 0 to x. Therefore, we want this from 0 to 12, we're going to use the CDF. So notice Poisson CDF, lambda, and I put many, many decimals here because I'm calculating x is 12. Paste, if you enter it, you come up with this number. And what is the answer that you want? 1 minus this number. 1 minus this number. And that's 0.0024. So in essence, 0.24%. It's a very small possibility. Could somebody read this, please? Part C.
To complete the chart at the right, the first column lists the numbers of touchdowns in a game. This is filled in already. The second column is for the predicted probability that a game chosen at random will have that many touchdowns scored. Calculate these values, round these values to the closest 0.0001. The third column is for your best prediction about the number of games during the season that had that many touchdowns scored. Round these values to the closest whole number.
Excellent. So we have from the previous page, everything that we have done, the probability of x using this formula is 5.1055 to the power of x e to the power minus 5.1055 over x factorial. So for example, plug in 0. I can put 0 here. And I hope you realize that this to the power of 0 is 1, 0 factor is 1. So in essence, it's e to the power of minus 5.1055. And the answer it gives you, or if you go with the Poisson PDF, you have the lambda, you have x equals 0, and you do get the same answer here. Now, I'm multiplying this number by 256. There were 256 games, and I get this number. So because I want to put the number here and here. So I put the number here. And by the way, I don't want to pay attention to this yet. I want to put a lot of decimals on purpose. And then this number, if it's multiplied by 256, is this number. But this number has to be rounded up to number 2 because we want to round it to a whole number. See, so the answer is 1.55 rounded to 2. This one, we want to go with the 4th decimal. So I didn't do that, but the 4th decimal changes to 1. So this is 0.006. After 6 comes 0. Next to it is 6. We change it to 1. So that's, I didn't change it on purpose because I wanted to show you. What about 1? Let's go with this formula and replace the x with 1. And then multiply it by 256. So this number goes here. And if you multiply it by 256 goes here. Let me do one more. Let's change this x to 2. This number goes here, multiplied by 256 goes here. So take a look. This number, 0.0309, and then since this is 5 next to it, 6, we change it to a 6. This number is 0.79025, and it actually is just, I changed this one to a 5, but you don't have to, just 2, because if you're going to go with 4 decimals, this is really 2. And then we're going to multiply by 256. When you multiply by 256, this becomes 7.9, and you change it to 8. This becomes 20.23, and you change it to 20 because you want a whole number. So again, for this one, for this number, you can drop this one because it's 0.790. We want 4 decimals. 1, 2, 3, 4. I just wanted to show you with more decimals, but you can do it accordingly. All right, so again, follow the number of decimals they ask you, just to be on the safe side, but it's easy to see what happens. That's it for today.